I think we'll go ahead and get started. Good afternoon, everybody. I'm Sharon Megdal. I'm Director of the Water Resources Research Center here at the University of Arizona. And it's my great pleasure to welcome you all today to our water webinar entitled A Guide to Key Findings of the Arizona Tri-University Recharge and Water Reliability Project Report. I would like to ask you to please mute yourself during the webinar. After the presentation, we'll have some Q&A, which I will moderate. We invite you to place questions in the Q&A at any time, in the chat, rather. And we will be recording this and posting the recording along with the PDF of the slides, usually within 24 to 36 hours after the webinar. We do go for 75 minutes, which means we'll go to 15 minutes after the next hour. And we again welcome your questions toward the end. I do want to respectfully acknowledge that the University of Arizona is on the land and territories of indigenous peoples. Today, Arizona is home to 22 federally recognized tribes, with Tucson being home to the Otham and the Yaqui. The university strives to build sustainable relationships with sovereign Native nations and indigenous communities through educational offerings, partnerships, and community service. I do want to bring your attention to a couple of other upcoming water webinars, and we'll be adding to this as the semester goes along. The semester here is starting August 24th. But on September 8th, we'll have a water webinar looking at some of the issues relating to data centers and how they operate and their related water use. We also have a water webinar scheduled for late October on tribal sovereignty in the Colorado River Basin and beyond. And of course, we wish to continue reminding you about our annual conference, which is scheduled for April 26th and 27th. So again, welcome to today's webinar on the what we call the A-Tour project, the Arizona Tri-University Recharge and Water Reliability Project, and the reports that have been issued from it. We have a great lineup of speakers, so I'm going to provide very limited introductions of the speakers. More information is on the website for the water webinar. We have today Neha Gupta, who's an assistant research professor at the Arizona Institute for Resilience here at the University of Arizona. We have Kathy Jacobs, who is recently retired as director of the Center for Climate Adaptation Science and Solutions, also within the Arizona Institute for Resilience. We have Caelum Mroczek, who's a postdoctoral researcher, also at AIR, which is how we commonly refer to the Arizona Institute for Resilience here. We have our colleague Abe Springer, professor, School of Earth and Sustainability at Northern Arizona University. And then Tianfang Xu, who's an assistant professor, School of Sustainable Engineering in the Built Environment at Arizona State University. So without further ado, I'm going to turn it over to Kathy. We'll have the flow of speakers with Kathy and Neha coming back later on, and then I'll come back to moderate the questions. So thank you all for being here. Thank you, speakers. And Kathy, the floor is yours.
Well, thank you very much, Sharon. We really appreciate this opportunity to share the work that we've been doing over the past 3.5 years or so. As many of you already know, this project was funded by the Arizona Board of Regents across the 3 universities at the request of the Arizona Department of Water Resources. The whole idea of this project was to work collaboratively across the 3 universities to help answer some water-related questions across the state. And of course, the timing of this project turned out to be even more critical than any of us anticipated. We did have 45 people working on this project, including 15 faculty over the time frame, which is a truly amazing fact. And we've also been collaborating and engaging with around 90 organizations and individuals across the state to try to make sure that what we did was as useful as possible. We always share the stage with Tom Meixner, who was the original PI for this project. We like to acknowledge his legacy, which was really very impressive. And as many of you know, he passed away tragically near the beginning of this project. Next slide. So the basic framing for this project came from the Arizona Department of Water Resources. The question is, where and how can we capture and recharge water that is currently lost to the atmosphere or generated relative to enhanced runoff to enhance our enhance our groundwater supplies. And our entire project has been built in the context of the existing water management structure across the state. We have tried to take into account surface water rights, groundwater rights, the existence of all the AMAs and INAs. The whole context within which we're operating is essentially the real world, trying to set up information that people can use to make better decisions going forward. Next. So in thinking about this, we decided we needed to focus primarily on the natural hydrologic cycle. So we did not include in our assessments the demand side of the equation, but rather the supply side of the equation. That's primarily because we're trying to look at ways to find new water that is not currently being used in any system across the state. And by new water, we mean water that would otherwise have evaporated. So when you look at the natural hydrologic cycle, the main components of it are precipitation, evapotranspiration, which is a combination of evaporation and the water used by plants, which is called transpiration, recharge, and runoff. And as you can already see in these graphics, there's a strong pattern across the state that's connected to where the Mogollon Rim is, which is sort of extends from the southeast up to the northwest of the state. That's where the vast majority of the precipitation and the evapotranspiration is. We also developed something called a subsurface infiltration index to start trying to overlay the kinds of fundamental features that affect whether or not recharge can take place and where it is it's easiest to get water below the surface and down to the aquifer. Next. So we thought about this in particular in the context of land management strategies. In other words, how can we modify the things we're already doing across the landscape, whether it's forest management or it's development of new urban areas? How can we think about enhancing the capture of water and the recharge of water below the surface in the context of those land management strategies? So, for example, forest thinning can be done in various ways and is already progressing across the state. There are ways to do it so that it can actually enhance recharge as opposed to enhancing evaporation. And in addition, there are other examples across the state, such as the San Carlos Apache tribe's restoration efforts to control erosion have also enhanced recharge along the way. So we tried to incorporate not only things that people are already doing across the state, but also ideas from across the world that might not have been taken into account up until now. Next. So I mentioned the fact that there are strong patterns across the state, and we have a lot of complexity. Essentially what we see is because we have an uplifted area across the center part of the state from the Grand Canyon all the way down to the southeastern portion, we have a lot more evaporation and precipitation in that area. We've tried to consolidate the patterns by doing it by physiographic province, the Basin and Range province, which is the southern part of the state, mountains interspersed by basins, the Colorado Plateau, which is the whole northeastern part of the state, and then in this transition zone I've been mentioning. Further, we have many landscape types: forest, grassland, urban, rural. We've tried to address many different landscape types in the various recharge options that we've identified. Next. Just because not everyone who is joining us today may understand all that there is to know about aquifers and groundwater recharge, we have exactly one slide to try to summarize this. Groundwater recharge is influenced by many factors. If there's a very long distance between the surface and the aquifer, that can slow down the recharge and also impede it in various ways, especially if there are subsurface properties like clay layers that stop the water from percolating down through what we call the vadose zone, the unsaturated zone. It also matters how often it rains or how often the area is saturated, and whether there's a significant ponding time. If it remains wet with water pressure downward from the top, that helps a lot with enhancing the recharge rate. We see lots of variation through time and history in terms of the amount of water that gets recharged. And in addition, the amount of time it takes to go from the surface down to the water table itself can vary from days to millennia, depending on how the geology works in any given location. Next. So I'm now going to turn it over to Neha, who was the project manager for this entire effort. And she's going to be talking about the key findings, at least a few of our many key findings going forward. Thank you, Neha.
Thanks, Kathy. So I'm going to go over, as Kathy said, some of our key findings. We'll be covering a number of them throughout this presentation, but I'll also note that in our final report, which we'll pop a link into the chat in a moment, contains dozens of key findings related to distinct research projects that were conducted as part of this study. One of the major things that we did in this study was a statewide hydroclimate assessment, which underpinned some of the information that Kathy just presented in our introduction. So this was a modeling framework that used both historical and future data that were fed through NOAA MP, which is what we call a community land surface model, as well as the national water model. These are the models that we use to actually partition out those water balance components for the natural hydrologic cycle. So what we did was come up with these estimates for both the historical 1980 to 2020, as well as project them down to 2100 using a series of climate models. And then we also summarize this data not only across the state, but developing groundwater basin profiles summarizing this information for all of the 51 groundwater basins defined by DWR. So in terms of our natural water balance, I like to say Arizona is a hot, dry state. We see that less than 3% of the rain that falls across the state becomes recharge. Really, most of that, 95%, and in some cases over 100% of that water is lost back to the atmosphere through evapotranspiration. Kathy mentioned that evapotranspiration, is a combination of the water that's lost directly through evaporation through the soil, as well as water used by plants, which we see as transpiration and canopy evaporation. These are numbers that our models are able to parse out, so they're also included in our groundwater basin profiles so that we can understand of the water being lost to the atmosphere, about how much of that is being, used by plants. And one of the take-home messages from this is just that very little of the water that falls across the state actually gets into, what can be considered recharge or potential recharge. But our take on this is that by even changing the amount of water lost to the atmosphere by a small amount can result in relatively large increases of the amount of recharge. In terms of where recharge occurs in Arizona, there's a strong pattern, again, associated with the physiographic provinces that Kathy introduced earlier. So in the Colorado Plateau, this is an area with a lot of bedrock geology that contains faults and fractures and karsts. So there's a lot of really focused, rapid recharge that can occur in this area. A lot of the recharge in the state occurs along the Mogollon Rim, so that transition zone that cuts across the state, That is where we see the most recharge across the state and is also our most productive watersheds in the state, the Salt and the Verde. Of a special importance in Arizona is the White Mountains, which are the headwaters for the Gila River, the Salt River, and the Little Colorado River. Within the Basin and Range province, you don't see a lot of recharge on average. So again, this is on average across 40 years. You do see some hot spots in the Sky Islands within the Basin and Range province, but overall, what we tend to see in this hotter, drier part of the state is recharge associated more with extreme events. So recharge is not evenly distributed across Arizona. It's highest in the mountains, it's lowest in our southwestern desert regions, and the amount of rainfall that becomes recharge or potential recharge can range from less than 1% to over 10% of rainfall. In terms of when recharge occurs, this also varies across time. We see the most recharge occurring in the winter months. This is where we see that especially precipitation exceeds ET or that atmospheric demand. You also see a strong signal associated with snow and melting snow in the time when we have the most recharge. In the summertime, we do see the most rainfall coming, but we also see the highest atmospheric demands, resulting in relatively little of that rainfall becoming recharge. The data that we're providing to you are really based on models. And with all models, there are strengths and then there are trade-offs or limitations. And we like to be very transparent about these up front. One of the strengths, or many of the strengths that we see with these models, is the ability to conduct these analyses at scale and use them at a higher screening level to think about where some of those highest recharge areas might be. These models also allow us to look at how conditions change across space, across time, across seasons, to input climate change projections to see how things might change. But again, these are relatively coarse scale modeling efforts at 1 to 4 kilometers. Within these models, they are not developed as groundwater models. These are land surface models that are highly developed, but they don't include, karst and fractured rock flows. It doesn't include human activities, as Kathy mentioned, including groundwater pumping or artificial recharge. And so these models, again, are not intended for site-specific information, but can provide a starting point for more detailed site and regional analyses. We did look at the influence of climate change by downscaling about 14 global climate models. Overall, what we see is temperature is consistently predicted to increase, and that recharge is overall predicted to decrease, coming to pretty close to zero by 2100 on average. We do see the largest decreases in recharge within the Mogollon Rim in those high mountainous areas. We see these biggest decreases because there's the most water to lose, essentially. This is especially concerning given that they are the most productive watersheds in the state. So this is something that we want to keep in mind, and especially the role of extreme events and intense precipitation events that may be able to counteract some of these decreases on average recharge. We also see that when we look at our climate change projections, that we see a groundwater storage anomaly decreasing. So we interpret this as a change in groundwater storage over time, and we see that decreasing. Our models are able to predict this, we think, relatively well. We see pretty high agreement with the GRACE satellite data. We also see this groundwater storage anomaly being a major part of the overall water loss from the system across the state that is predicted primarily due to warming effects. We also looked at changes due to both climate change and land cover change as vegetation shifts and moves into different ecological niches. So we combined about 5 global climate models with some changes in vegetation. Overall, the changes that were simulated were changing forests and grasslands, to more of a shrubland scenario. So forests becoming more of grasslands, grasslands becoming more of shrublands. And you see these changes primarily occurring in our forested areas along the Mogollon Rim, and then some of our southern Arizona grasslands as well. Overall, what we see is that there is a major signal due to climate change. Especially in higher elevations, we see increases in ET that are projected, and also decreases in recharge due to more of that rainfall getting partitioned into ET. In lower elevations, we see that the changes in ET largely follow predicted changes in precipitation, given that evapotranspiration is already limited by the amount of water available in these places. So the take-home message is the climate signal does dominate what we see, but there is still a small land cover change that we also see. So now at this point, I'm going to turn it over to Dr. Abe Springer at NAU to start talking about baseflow and some of the other key findings of our report.
Thank you, Neha. And based on some of the comments I'm being distracted from in the chat box, remind you that this is a statewide level assessment that had to rely for as much as we did on largely existing data and information. And the work that's largely been done by the team of students, researchers, and faculty on the project has already been put in the peer-reviewed literature as the process of getting there. Our presentation today is barely touching the surface of a few key points, so we encourage anybody who's interested in diving in deeper to look at the links that are provided for our final project report and links to many of the other products we have, from story maps through links to publications and other things that describe the very interesting and detailed work of the project team through time. I wanted to talk about a few things about understanding the distribution of recharge and its discharge into our groundwater systems of the state. It's important to look at where recharge is distributed based on where it discharges, which is a term that we call base flow. Base flow is the amount of stream flow that's supported by groundwater flow. And most of our perennial streams in the state only flow continuously from groundwater, except those that are below wastewater treatment plants or at outfall from dams or reservoirs. So we did a detailed assessment. This was part of Caelum Mroczek's dissertation, who you'll hear from here in a little bit. And to put this in context, many of you have seen the Department of Water Resources water facts numbers for the state of Arizona. And the department indicates that of the state's water supply, 41% comes from groundwater and 18% of the state's water supply comes from in-state rivers. One of the important take-home messages I'm sharing with this slide is, of the flow of the rivers within the state, a third of that flow of these rivers is supported by groundwater flow. And that groundwater is largely contributed by melting snow on the Colorado Plateau and on the Mogollon Rim. And it's lowest in the low elevation areas that have low amounts of precipitation. Next slide. So we wanted to better improve and understand how we could enhance recharge across the state around the bounds of where precipitation is distributed and how land is used and managed. And we've coined this new term called opportunistic recharge enhancement. And it's more than small engineered managed aquifer recharge projects that probably most of you are familiar with or have worked with or designed. So, having a wastewater recharge facility or a stormwater detention basin. This is an option that's at the interface between those and full landscape management. So the goal is to look at the considerations on how recharge occurs around primary land and water management goals, and to try to find ways to increase the way that water is made available through them through approaches that are interdisciplinary, cross-disciplinary, and scalable. And we'll give some examples of these through what we've already been talking about is the process of forest management. Arizona contains the largest contiguous stand of ponderosa pine in the world. Many of you know the large-scale forest restoration process that's in progress, the Forest Restoration Initiative. And the work of this team, especially our landscape and plant people, really helps inform and describes how you could improve that type of large-scale management for the benefit of hydrologic systems. This can also be done for other types of land management work, such as post-wildfire management or large landscape scale road works done by some of our state and federal land managers for their roads. Next slide. So the framework that we've published for this opportunistic recharge enhancement is shown here schematically, and I don't need to read through this. Many of you can look at these summaries in our documents, but we provided the guidance and the blueprints for people to look to these opportunities to better capture water in the hydrologic systems of the state for benefit of putting it below ground and in recharging it. And we've identified some areas that are commonly not thought of that are important to understand and know, such as the karst terrain of the state or the geology of the state that's favorable through enhanced flow through faults or fractures in the rocks. So we've made some of the first statewide maps of the lineaments, the linear features that are faults and fractures of the state. And we're working to develop the first map of all the sinkholes in the state of the Arizona that could be used for enhancement of recharge. Next slide. And just as an example, the picture in the upper left is a structure that was built after one of the recent fires up on the Coconino National Forest. These are pond and plug structures that are designed to mitigate catastrophic flooding after catastrophic fires, but they have the benefit of slowing down water, spreading it out, and enhancing recharge in post-burn areas. So these are things that can be deployed and have been deployed by some of our land managers across landscapes. There's some great examples from the borderlands in southern Arizona of implementing these types of techniques for hydrologic benefit. The figure on the upper right is a schematic for looking at ways when you're doing road maintenance or activities on landscapes of considering how to design that to enhance slowing and capturing water to enhance it for recharge in the systems as well. So this kind of work can be implemented through changes to different agencies or organizations' plans for how they manage systems. So next slide. These, and again, as we've worked on these projects at statewide levels, this mosaic of maps you see here on the left is our statewide assessment of finding areas suitable for enhancing recharge. And dominantly in the state, there are areas that are dominated by snow and are dominantly underlain by limestone or similar types of carbonate rocks. This is a type of geology in a landform that has generally been unrecognized and underappreciated in its hydrologic role in the state of Arizona. And this diagram here on the upper right of this slide gives you an example of the ways that these types of carbonate rocks, limestones, can enhance and improve the rapid recharge of water into the subsurface. One of the myths of the state of Arizona is all our water is millions of years old and it takes millions of years to get down thousands of feet. The truth is, in these types of terrains where you have sinkholes, faults, and fractures, water can travel very quickly on the order of days, weeks from snowmelt down to the subsurface. What our team has also shown is that due to the vagaries of our climate, the timing when we get snow melting or enhanced runoff, it is very ephemeral in time. So it's important that we understand that we try to capture it on those times when it is available, but it can be quickly put into the subsurface. And before the chat box fires up with questions about water quality related to that, generally melting snow is very good water quality. And I'm not talking about water infiltrating in other areas. These are areas up in forested areas or other places, and they're generally extraordinarily high quality water. When we do tracer studies or look at things recharging here, the water quality is dramatically improved from snow melt or other types of very quick, rapid recharge. Next slide. And it matters on how the forests and lands are managed. Some of the members of our team of the project have published this work that helps inform how you do forest treatment. So you don't want to have random cutting of trees and thinnings. Our scientists have very good recommendations on prescriptions to optimize the sizes and shapes of openings, that optimize shading and minimization of sublimation of snow during warm, dry, sunny periods in between snowmelt events. Next slide. I think I'm turning it over to Tianfang now, who'll be highlighting some of the work from our urban things done on the project.
Thanks, Abe. So we've been up on the plateau and in the forests, and as Abe mentioned, I want to bring us down to the valley floor and the urban areas where the hydrology looks very different. Much of the ground in a city is pretty much impermeable, with roofs, roads, and parking lots. Rain that would have once soaked down now runs off almost immediately. And that's a flood problem before it's ever a water supply problem, and Arizona cities have been managing floods for decades. The figures show the two pieces of infrastructure that are common in Phoenix. The first are the retention-detention ponds. Those basins are sometimes landscaped, and we often see them in parks and subdivisions. A runoff is routed in ponds and infiltrates, although some is lost to evaporation. The second is a dry well, which is a borehole that takes runoff below the land surface and into the beta zone, bypassing the root zone entirely. Both are almost everywhere in Phoenix because of existing stormwater management mandates. Chandler, for example, designs for 100% capture of runoff. What nobody keeps is a master map of all of this across the AMA. So we built one for Phoenix AMA by detecting retention ponds from LiDAR. There are more than 12,000 of them. We then use design code and actual precipitation data to estimate how much water each captures, along with over 40,000 dry wells. Put together, this infrastructure captures about 94,000 acre-feet a year across the Phoenix AMA, and most of that water gets infiltrated. That 94,000 acre-feet is roughly 13% of groundwater pumpage. Ponds do about 80% of it, and dry wells about 20%. Next slide, please. The map on the left shows where that capture happens as a percentage of the runoff generated. Capture is very uneven, and the high capture areas, the yellows and light greens, are the relatively newly developed parts of the valley, built under modern stormwater requirements. The darker areas through the older urban core predates those codes. So this map sort of points to where retrofits would buy the most for both flood risk and recharge potential at the same time. That pattern is also why we project it forward into the future. We ran it to mid-century under 5 downscaled climate models and a set of urbanization scenarios. If we hold land use fixed and change only the climate, and we go from 94,000 to about 110,000 acre-feet per year. In the high-end urbanization projection with new development meeting the stormwater management requirements, the total capture reaches 165,000 acre-feet per year. These numbers highlight the opportunity to transform stormwater from being a nuisance into a measurable asset for aquifer sustainability. Next slide, please. But capture is not the same as recharge, and this is where we want to be careful. The diagram on the left is a retention-detention pond. Runoff comes in, ponds on the surface, some got lost to evaporation, and the remaining begins to infiltrate. The panel in the middle follows the water down through the beta zone. Some is taken up by plant roots, some is held in soil pore spaces. A fine-grained layer can slow down the flux or stop it. Only the water that gets past the vegetation root zone and keeps moving downward will become deep percolation and eventually actual recharge to the aquifer. So the ATOR team used Hydrus 1D model, which is a numerical model, physics-based, to simulate those beta zone processes through time across a wide range of conditions varying in soil texture, how long and frequent water ponds, vegetation cover, to ask under what conditions recharge will actually be generated. The answers are in key message 3.1 in the final project report. Ponding is a very important control. Saturated conditions at the land surface presents opportunity to recharge, but the ponding duration we would need to actually initiate recharge is very site-specific. Soil texture matters a lot. Recharge feasibility declines substantially once clay content goes above about 20%. Which is why the report points toward basins designed for depths rather than area and designed for low clay soils. Next slide. The problem is that Hydrus model takes real expertise to set up, and a single run takes a couple of minutes because the nonlinearity forces very small time steps for the solver. This becomes a computational wall if we want to run it many times, and it's probably not something a city planner would want to sit down and use. So we trained an AI surrogate, a fast model based on machine learning to reproduce Hydrus. Inputs are ponding, soil texture, and vegetation. Outputs are infiltration and recharge. The AI surrogate reproduces Hydrus really closely, and one inference, that is one run, takes well under a millisecond. This is what makes an interactive web-based screening tool possible, and that's where we are taking this next. Next slide. Now, let me step back from the urban work to close on something that applies to all the opportunistic recharge enhancement strategies that ATOR team proposes. These strategies change the hydrological cycle, and the team put forward a set of guiding principles detailed in section 3 of that project report that aim to sustain and enhance habitat while we are enhancing recharge. The bottom line is that we definitely don't want to cut all the trees in Arizona. So maintain and enhance natural hydrologic system functions. We don't constrict floodplains and natural channels, and instead we replant with native species after a disturbance. Support healthy forests. Some of these are already mentioned by Abe. We recommend strategic ways to reduce fuels, to limit really big fire and the erosion that follows it, protect ground cover to slow runoff, and thin forest in patterns that shade snowpack to limit sublimation. Encourage recharge where the landscape already flavors it. For example, deliver runoff to ephemeral channels, to fractured bedrock and karst, provided that we consider water quality. Detain water in permeable soils near the source. And account for the trade-offs honestly. The natural habitat has its own water requirement. Recharge basins, retention ponds, they tend to silt up over time, and check dams and dry wells need to be maintained. These costs need to be considered in a plan from the start. So section 3 has the full set of guidelines, and we also have this appendix F, which pairs more than 50 ORE strategies with their constraints. And with that, I'll stop here and pass on to Caelum.
Great. Thank you, Tianfang. So I think we had a really good setup for some of the amazing science that has been done throughout this project with many, many people working on this over years. But we knew from the start that we wanted to take what we found and move it outside of solely the realm of academia. We wanted to ensure that this was something that would be able to be usable by water managers, land managers, and the likes. And so in supporting that, we have developed a number of decision support tools. I'm going to walk us through there. Next. So first and foremost, we have kind of an overarching decision support framework. It is a framework that has been developed in 10 steps, building from a site-specific interest. What is your water management objective? Where are you trying to do this? And on what scale are you trying to recharge water? And it helps you work through step by step all of the options that you might go through, all the way up through cost-benefit analyses and implementation. Now, the reason that we wanted to do this was to hopefully be able to allow you to walk through all of the good science that was done, know that this is well supported within modern current science, and then show you a way to actually do things from this. Now, one of the key things here is that this framework is provided not only as a PDF, but also as an interactive story map. So as we talk a little bit more about this will also be found in Appendix E in our final report. Next. The key thing here for the decision support framework is identifying the right strategy for the right context. Hopefully it's been made clear during this presentation that depending on where you are interested in a recharge project, be that in the Colorado Plateau, along the Mogollon Rim, or the Basin and Range regions, you're going to be looking at very different strategies. And those are going to be dependent not only on location, but on timing as well. And so we wanted to start to build on this process from the beginning, identifying where is it that you're looking at for your projects, and then what solutions might be possible for those locations in particular. The important thing here is that not all areas are going to have the same strengths as others. If you're trying to do a recharge project in the Basin and Range region, what you're going to do is going to look very different than if you were going to do a similar one in the Colorado Plateau. Now, the key here was to provide a flexible framework that has what we like to call like a menu of options. You can pick and choose depending on what you as the user are interested in. Next. So as I mentioned, the decision support framework is available as a story map. And this is really one of the ways that we suggest working with this tool. What this is an online interactive dashboard that has maps of the hydrologic cycle components, surface and subsurface properties, as well as our team's developed statewide suitability analyses. So we went ahead and did some of the work for you based on current best knowledge of how, what does recharge suitability look like throughout the state of Arizona? But if you are interested in a very specific location, you can then zoom in there and look at all of these different layers that have been developed through this project and start to see what your interests in your recharge project, what kind of options you have in certain areas. Next. As a part of the decision-making process, we developed 51 groundwater basin profiles. This was mentioned previously by Kathy. And what these are 4 pages total, 2 pages front and back, with immense information on both on each of these groundwater basins, all 51 throughout the state, so that you can identify the location that you're interested in, and then we can provide you with some of the science to make those decisions. So in particular, we have in the first 2 pages here, we have information on when and where recharge occurs naturally within those groundwater basins. We have summary statistics for the entirety of the basin. We have mean, annual, and monthly water balance features so that you can look at how things like precipitation or runoff change over time on average across the last 40 years. Along with that, we have then maps of the specific water balance components, very similar to what you would find in that decision support framework story map, but here then for the specific basin that you're interested in. Next. Now, the last 2 pages of these groundwater basin profiles then show you how the recharge in that basin might change in the future. Specifically, we looked at this with how that might change as a result of climate change. Again, this was looking at an ensemble model using 15 different climate projections. And along with this, because we know that some people are going to get lost and your eyes are going to glaze over as you're looking at all of these figures and graphs, we also have a narrative interpreting how that climate change may affect this recharge in each of these basins that has been developed for every basin specifically. And now all 51 of these profiles, I guess 52 because we also have one for the entirety of the state of Arizona, can be found in Appendix A of our final report, our groundwater basin profiles. Next. And as a connection piece to that, once you can start to identify what kinds of projects are we interested in? Where is that? What is viable in those locations? We came up with a set of over 50 strategies for enhancing your capture of water and recharge of water. And this includes opportunities, as well as we tried to think of what possible constraints might there be for these kinds of projects. And these are all organized by landscape type. So you can look at things in urban areas, rural and developing areas, agricultural landscapes, and then a number of different ones for natural landscapes. So here we have an example of a forested natural landscape. You might want to look at some form of fuel reduction or forest thinning. This is being done in many places across the state already. And so we identified what opportunities are there. Abe mentioned what some of these might be, such as thinning in a very specific way, but we do want to understand what kind of consequences might there be, what limitations are there. And so the exciting thing with this, found in Appendix F of our final report, is that we have provided some options to you already. And where possible, we're trying to tell you, what could be really beneficial here, but also what might you need to keep an eye out for potential consequences in the future. So hopefully, throughout all of these opportunities and this decision support tools that we've developed for water managers, you can take the strong science that we have developed, and you can see what all of that looks like by going through our final report. But then we've also tried to make this easier for you as an actual water manager to not have to wade through all of the extremely difficult and technical work there as well, and start to move towards solutions. Next. All right, with that, I'm going to be turning it back over then to Kathy.
Great. Thanks very much, Caelum. Thanks for the whirlwind tour of our products. Let's go next to the next slide. So we wanted to just summarize for you some of our highest level conclusions. You've heard a few of them already. For example, the idea that around 3% of the water that falls on the ground as snow or rain winds up as recharge, which is a really tiny percentage of the total amount of precipitation. But we also have some important climate change related findings where we were not aware previously how significant the impact of warming has already been on the water and storage across the state. And that is now pretty evident, and that's, of course, expected to accelerate. We're also interested to see that extreme events are consistently predicted to intensify, and they could provide recharge opportunities. It's actually much harder to capture very large floods than it is to capture, an average rainfall. But if you can figure out how to do it, large volumes of water might be available, and it is thought that climate change will enhance tropical storm type activities, particularly in the fall. So being ready for that kind of thing is an opportunity. A third major fact is one that Abe already shared with you, which is how important groundwater is to the surface water flows in the state. So it's really of interest to everyone in the entire state to make sure that we take good care of our groundwater aquifers and do the best we can to keep them recharged. One of the messages I find most compelling is this idea of opportunistic recharge enhancement, or ORE. The reason I find that compelling is what we're really saying here is that with relatively little cost, and of course that word relatively depends on what you're doing, we might be able to amend existing land management activities such as road building or forest thinning in ways that really enhance the recharge rate. And if that is true, just changing the priority of recharge in the objectives of land management activities across the state could make a very big difference over time. And as you heard from Tianfang, there actually are very large volumes of water being generated in urban areas. The question is really, how do you maximize the recharge of that as opposed to causing it to evaporate, which is what most flood control activities are focused on now. And then finally, possibly most importantly, all of our focus in this whole project has been how can we capture and store water, but not just for people, for the environment as well. What we see now is we are already drying up the aquifers. We're already affecting the surface water flows. We're changing the habitat conditions in the places that are the richest biologically in the whole state, which is the riparian areas. So what can we do through these processes that really enhance water availability to habitat at the same time as they're enhancing aquifer conditions? Next. So that was my high level one slide, and now I'm going to turn it over to Neha, and she's going to bring this home for you.
Thanks, Kathy, and thanks everyone on our team for speaking. So there's been a number of recommendations that have come out of our project. We're not going to go through all of them on this, but some of the high level ones are clearly the need for more information across the state. Really expanding the amount of data available can help us do better and more improved science and provide more data for decision making and management. This includes groundwater levels, ET flux towers, as well as groundwater pumping data, including more opportunities related to karst, mountain front recharge, flood, and floodplain management when there are regional reviews of opportunities being done, especially related to water resource management. We mentioned really thinking about multiple types of opportunities in urban regions, so protecting high recharge areas from development as a starting point, but also thinking about adding in dry wells in the urban retrofit, especially where there's limited areas available for larger flood control features, deeper retention basins over wider retention basins, as well as considering longer retention or ponding times that are allowed in basins. We understand there's a trade-off there with different types of public health concerns due to vector diseases, but this can also help get more water underground. And we also recommend really experimenting with ORE, that opportunistic recharge enhancement, applying that into management activities and starting to really discreetly think about recharge as a co-benefit, and also expanding partnerships related to all of these topics. This project is now in a 1-year no-cost extension, and we are also interested in continuing this line of work. So some of our next steps include exploring and developing opportunities to expand monitoring data across the state, including the role of community scientists and machine learning methods, increasing our science and research related to recharge opportunities due to extreme events, increasing the amount of data we have available to characterize how much water is getting underground due to different recharge strategies, making progress and steps forward on incorporating some of these findings into regional planning efforts, and continuing to communicate and disseminate some of our findings and products. All of our report products, tools are all available on our website, which I believe was also dropped into our chat earlier. And now we have made it to the end of our presentation and are happy to answer any questions. And so I think, Sharon, I will turn it back over to you.
All right. Well, thank you. And thank you all for a wonderful presentation, great slides, great explanations. You've got so much you could have covered. And so thank you for making this digestible for us. I want to note for those online, we will go to 15 minutes after the hour. We know we lose some people at the top of the hour, so that's just unfortunate, but we know that many of you will stay on, and we want to have time for questions and answers. So thank you. This is a little bit of a different panel in that it's large. I mean, we thank you all for agreeing to speak and speaking. And I know, as Abe indicated when he was making his comments, that he was perusing the Q&A, and I'm sure others here have been perusing it. Often I do the Q&A in kind of order in which they come in, but I'm going to do it a little differently this time. I'm going to start off with a couple questions I've jotted down, one of which actually came up in the chat. And maybe I can ask each of you to maybe pick out a topic that you want to speak about in terms of those questions that were asked there, because they're very far and wide, and cover both technical and urban planning issues and the like. So I'm going to try that and see if it works and do that. But I have a couple of different questions. First of all, I really like your term opportunistic recharge enhancement. That's a nice term. Actually, the acronym is also a very good acronym, and so I want to congratulate you for coming up with a term that has a good acronym and is easy to understand what the words mean. Kathy, you go way, way back, farther than I do in some of these water management issues, and we know that there long ago was talk about how do we capture some of these storm water flows, the flood flows, and that's coming up again. Tucson Water's One Water program. It's like that's the opportunity we have. We're pretty much making full use of other resources. And so the work that Tianfang presented and other things, really, we're almost coming full circle. And it's kind of like, okay, now it's more important than ever. How do we get it done? One of the questions I had that was asked in the chat was the question of downstream surface water rights. And to what extent did that come into discussion, or did you just skirt that? And Kathy, I don't know if you're the one who wants to take that or not.
I am. Yes. So from day one, we focused entirely on avoiding any impact on surface water rights downstream. And in order to do that, you have to focus on essentially new water that's being lost to the system that is not reaching the beds and banks of natural or artificial channels that are currently serving surface water. So that was part of our agreement with the Department of Water Resources from day one. We have deliberately avoided any impact on surface water rights. And I think everybody now acknowledges how important that is. From a political perspective, nothing in this report is intended to upset the existing apple cart.
So that's great to hear. You mentioned ADWR at the outset and just now in your response, and I am so very much intrigued by the 51 groundwater basin fact sheets. And I had a question about just sharing of the information. Is there going to be a link on ADWR's website to these fact sheets, or because it seems to complement what's coming out in the water supply, the groundwater supply and demand studies that are coming out for each. So I was just curious if there was going to be any sharing of information from the ADWR website.
Well, we can't predict exactly what they will do, but our expectation is that they will direct people to ours. That being said, we deliberately designed this whole thing to support their supply and demand studies because we knew they didn't have those natural cycle information for each basin in the state. And all of a sudden now we've got this amazing modeling capacity that never existed before. This is all essentially new in the last 10 to 15 years to be able to do this kind of work. So it's very sophisticated. We know that they intend to use our work as the foundation of future activities. We don't know exactly which ones, but I'm pretty sure they'll direct people to our website rather than posting it themselves.
Yeah,
but they did announce our results.
Yeah, and that's what I was asking really about. I don't expect them to put each one of those on there, but if they can direct, because it's so complimentary and has some great information, which, as you suggested when talking about it in your presentation, I don't think people are going to sit down and read 51 of those, but as people focus on this groundwater basin or another, as Neha has done a lot of in the work she's been doing in the rural groundwater basins, the workshops, I would think it would be very, very well received to have that information. I'm just going to ask one more question, and then I'm going to tell you, Abe, I'm going to call on you next to see what question or questions in the chat you would like to answer. And then maybe Tianfang Xu for the next one. And then we'll go around and, if you'll be brief, we'll have time to cover most of the questions. I know, and you mentioned early on that you had many stakeholder groups, meetings. I know you had grad student that was the grad student's job to help with that. And I'm wondering, as someone who years ago served on the ADOT board, and then also years ago served on development of a recharge project, a managed aquifer recharge project that involved the flood control district, that sometimes questions will come up about whether this sort of thing fits in with their mandates. So I was wondering to what extent agencies like ADOT or any of the flood control districts were involved, and whether you got a good sense of it fitting in with their future activities. And I don't know who's the best person to answer that.
I think that's a softball for Neha. We'll let her take that one.
And I didn't mean it as a softball, but if it is, that's good.
Well, I think the easy answer for that is that we've been really focused on the role of flood control districts in increasing recharge. And we held a workshop with flood control districts across the state on this very topic. We also have a little summary brief about that workshop that we have on our website that we can pop into the chat. But the flood control districts, and now expanding into the roads, thinking about transportation systems, are some of the key areas that we've been looking at for, ways to increase recharge, especially in our urban areas, or roads that cut across hill slopes, roads that need maintenance out in the forest. There's all kinds of opportunities.
Yeah,
We also spent a fair amount of time supporting tribal questions, and we had a workshop for tribal interests as well, and reached out to all the tribes in Arizona to see what kinds of questions they might have. So we had a pretty substantial strategy for engagement, in some cases as in groups, and in some cases individual organizations.
Yeah, sometimes it really just takes some leadership or different vision to get people to think, because I remember talking to some people here on the university campus, whereas the kind of design and engineering typically was just get the accumulated water off campus, and there was no kind of rainwater harvesting or anything like that. And that's changed over the last 20 years or so substantially. And so sometimes it's a matter of a change in approach and thinking. So anyway, Abe, I'm going to call on you to see what of those questions in there you would like to address. There have been some great questions asked there.
Thanks, Sharon. I was going to address them kind of generally. I know many of you on the participant list may have never met me or know me because I'm buried in Flagstaff, not down in the major urban areas. But I'm in my 33rd year in the university system in Arizona looking at hydrogeology. And one thing this statewide project I thought brought home to us is issues of data quality. So I saw a number of comments in the chat box about data. And unfortunately, there's a lot of data in this state that aren't useful for these types of assessments or analyses. And most of you, I've looked at some of the participants on here, this is recent that we have, there we go, a device in our hands that gets us accuracy to 1 meter or less. And most all the spatial data in the state was collected before there was GPS. And it's very poor accuracy and resolution of data that we have for a lot of things. The other thing that Neha showed you is we have almost no continuously recording depth to groundwater wells in most of the basins of the state that we can use to assess the timeliness of recharge events in these types of systems. So by us evaluating the quality and distribution of data across the state, I think some of the key recommendations are we discovered these gaps and deficiencies in the data. And this climate model tool that Neha showed you pretty matter-of-factly is pretty tremendous to have this statewide model predicting recharge. And the other thing out there, I know there's probably a few groundwater modelers on here, that is not a deterministic mod flow model. We didn't derive recharge by doing a statewide map of groundwater recharge. And as a deterministic modeler most of my career, I've been amazed and impressed by how useful machine language learning models are. Caelum did this for his dissertation on understanding and looking at stream flow, and they have as different uncertainty and things on it, but in some ways they provide us better insight and understanding of systems than some of our traditional deterministic types of models. So I didn't directly answer some of those questions, Sharon, but I wanted to give you some insight onto some of the types of detail behind some of those questions that were out there.
Yeah, no, that's great. And Caelum, you did your PhD with Abe, is that right? You did some of your PhD work, and now you're here at the University of Arizona as a postdoc, is that right?
Yeah, that's correct. I had the opportunity to do my entire PhD as part of the ATER project, and I was lucky enough to be involved kind of from the beginning to the end. And when I was graduating, there was an opportunity to continue this for one more year and see where it could go from there. And so,
Great.
yeah.
So I kind of said I wasn't going to direct questions, but I think I can't resist doing some of that, and I am going to do some of that. And bring in some things that are definitely from the chat. But first, build on what Abe just said. You have a tremendous amount of material on your website. I mean, you are to be congratulated for not only doing these great technical studies and getting some peer-reviewed articles out there, but getting all kinds of other documents on there. Many of the people, and it's been acknowledged, I think, in your presentation and along the way, who need to kind of or want to understand this information are not technical modelers, right? We know that. And I will just say from my own perspective, this whole thing with machine learning and what it means and what it does, if you haven't done a little bulletin on that, maybe you want to help us understand what it is and then know you're using it, because I think people can really understand that. So Abe, I appreciate your bringing that up. I'd like to go maybe, I don't know if Tianfang is the right one, and that is, there's questions about urban settings and dry wells, and particularly a good friend, Trace English, has been asking me, and I referred him to Neha, questions about the potential for dry wells, and there's less of that going on in Tucson than the Phoenix area. Maybe you could say some words, some more about that. And your slide on that was great. I mean, thank you for that.
Thanks, Sharon. Sure. I think Tress and I have connected before, so it's good to see you again, Tress. Yes, I think Phoenix AMA has more than 40,000 dry wells, which accounts for probably 95% of all the dry wells in Arizona, per the registry at ADEQ. I guess I'm going to speak from the experience working on Phoenix AMA, because that's where I'm located and where my work in this project has been focused on. I felt like there are definitely lots of potential with dry wells for a couple of good reasons. So first, they do have a very small spatial footprint, which makes them very suitable in tight spaces in urban areas where we just don't have enough areas to build a retention pond. And second, it does direct water bypassing the root zone, so therefore substantially reducing loss through evapotranspiration. However, it does have some precautions that we need to be aware of, which are they could be inducing some potential of contamination because of that reduced travel time through the Veda zone. But there are strategies that we can use to kind of constrain that risk. So from our analysis in Phoenix AMA, dry wells accounts for about 20% of that total captured and filtrated recharge. And largely, they're often used in parking lots or sometimes in combination with the landscape detention retention ponds. Again, so especially when there's tight space and you just can't have a big enough pond to hold that much stormwater, say, under existing design code. So I personally, I love dry wells. I noticed dry wells the first time when I came to Arizona. I became interested in that, even though I'm a groundwater hydrologist by training. So yeah, I'd be happy to talk more offline.
Right, great. Thank you for that. Neha, did you or anybody else want to add anything? We're down to 5 minutes left, related to any of these urban dry well questions.
Well, the one thing that I popped into the chat, because I know we always ask ourselves in Tucson why we don't have more dry wells. I don't have the definitive answer on that, but I do remember someone telling me a while ago that it had to do with our higher sediment load and our stormwater, things like our caliche layers underground. So there are also different types of complications when it comes to dry wells that they're easily clogged by sediment. They require, what can be sometimes expensive maintenance depending on how many you have to do. And you can only get water down into the aquifer if you don't have something impeding that water along the way. So we like dry wells in the urban environment, and there's a couple of complexities to navigate.
Yeah, thank you for that, Neha. I remember years ago when the Kino Environmental Restoration Project was all being developed, there was a hope that there could be more recharge done as that water, and I always get confused between retention and detention basins, but it turned out it was caliche and clay there, and it just wasn't suitable for recharge. So it gets to, those underlying geological conditions. We're down to 4 minutes left. And so I'd like to put out there, other things that you saw in the chat or wrap up comments that you'd like to offer before we close.
Hey, Sharon,
I'll jump in. Oh, go ahead.
Sharon,
Sorry.
I just posted a note in the chat box that I forgot to mention. I specifically had Caelum putting in a picture of us dumping dye in one of our tracer studies as part of this project. But at NEU, as part of this project, we've developed a tracer study laboratory to better help understand and address the time it takes to get recharge into the subsurface. And so we'd be happy to, I'll point to Caelum. Caelum would be happy to talk with you about looking for opportunities to transfer that technology to questions you may have related to that.
Okay, thank you for that. Kathy, you were going to say something.
Yeah, I just wanted to emphasize a point that I don't think has come up so far, which is really the educational component of this whole team approach. I don't think many people who were on this team have ever had the opportunity to work so closely across universities or across disciplines, certainly not working in an applied context. And so I think the learning that went on in terms of the management of this program and the numbers of people involved and keeping all the wheels and the cogs oiled and making sure people were generally going in the same direction was a pretty major effort, but also I think a pretty big success of this project, because it is in fact the most complicated and technical project in my entire career. And so that really says something, given that I just wimped out after 45 years. So anyway, I'm really pleased with how things have come out and all of the amazing people that we've had a chance to work with. I think it's been great for our students in particular.
Well, thank you for that. And Kathy, I think that's a perfect way to wrap up our session. As someone who was in that early discussion with ADWR when multiple projects were being presented to them, and that this project was selected, and to see what you've accomplished on so many dimensions, you really are to be congratulated. Kathy's this is a great culmination for you, because you have led so many different projects over the years, and that this was done. And you remember 2 years ago, we had you present a panel at our annual conference, which we dedicated to the memory and legacy of Tom Meixner. I think Tom would be very proud of what has come out of this project. And there have been other tri-university projects funded. One of the more recent ones is one on agriculture in dry lands that is really getting going now. It was funded in the spring. And so you've set a high bar, I think, for others working on these projects. So thank you for the presentation today and all your work. And thank you all for being in attendance. And we will get this, the recording posted probably by the end of tomorrow. If not, then tomorrow's a Friday. So we'll gear to get this done by tomorrow, barring some unforeseen circumstance. So thank you all and have a good day.
Thank you for hosting us and all of your kind words.
Thanks, Sharon.
Thank you.